Welcome. This is a recorded session of the Post-Quantum Cryptography Conference of the PKI Consortium, which took place in Kuala Lumpur, Malaysia. This conference is made possible through the support of the PKI Consortium Post-Quantum Cryptography Working Group and our sponsors SSL.com, Entrust, Keyfactor, HID, and Crypto4A. And with exceptional organizational support from SSL.com, Keyfactor, Logius, POS Digicert, Baker Tilly, MSC Trustgate, and Digitoris. Join the discussion. Join the PKI Consortium. Go to pkic.org/join.
Well, good morning, everybody. All right. Just checking to see if everyone's had enough coffee or those lovely Danishes. I used to think, as an American, when I died I was going to come back as a European to get all your vacation time. But now I think I'm going to come back as a Malaysian so I get to eat all this great food. It's been fantastic. Welcome and thank you for attending this breakout session. My name is John Busali. I'm the moderator here today. I think we have a great assembly of speakers, and I'm not going to take too much of their time to continue the discussion of post-quantum cryptography and effective methods for migration and transformation. So joining us to start off today's conversation, we have Alessandro Amadori. He's a cryptographer at TNO, the Dutch research agency. He's got his PhD in cryptography. He's contributed to several publications. One of my favorite is the work that TNO has been doing on migration handbooks. I'm sure he'll mention it. If you have not seen that, I think it's in its second edition. It's one of the more valuable resources that I've come across for industry. So without further ado, Alessandro.
Thank you, John. You're too kind. Welcome everybody. Today I wanted to talk to you about one of the projects that we've been doing at TNO on trying to apply cryptography to real life use cases, and I wanted to present you a project that we're working on electric vehicle infrastructure, and the quest for migrating such an infrastructure to post-quantum cryptography. So yeah, the project is called the DITM project, and the infrastructure that we were trying to migrate is called the EnergyPod, and we wanted to talk about a little bit the struggles that we have had, or at least the results that we were able to achieve during the project. And I'm gonna present you a use case, which is a protocol that is used a lot in electric vehicle, and the proof of concept, and a couple of takeaways that you have learned during the work on this project. So, what is the DITM project? That DITM stands for Digital Infrastructure for Future-Proof Mobility. The T stands for future-proof, but it's Dutch, and future-proof in Dutch starts with T. There is an introduction. There is an intro video. I put the link. I tried to put a QR code, but it kept expiring, so I thought it was going to be much faster to put a link. So the DITM project is a research project led by Brainport Eindhoven in the Netherlands, and it was made possible by the Ministry of Infrastructure and Water Management. And it's a 4-year project that consists of 60 million euros. There's 20 partners. There's a lot of them. You can see them in the slides. There are too many to mention. And it's co-founded by the DITM partner and the European Union Next Generation. So what is the goal of the project? It's about autonomous driving and electric vehicles, and it has 4 main goals. The first one is the construction of autonomous functions for automatic driving that relate to connectivity, localization, maneuvers. So the fancy things that you see online on maneuvering, navigation, parking, etc. Then the construction of an energy exchange system, which we call the EnergyPod, which is a crucial link between the critical infrastructure and the electricity grid and the infrastructure that relates to the electric vehicles. A map production system that keeps updating the navigation depending on the old information that are being collected from the autonomous function and the EnergyPod. And a validation lab. So it's just a testing lab where you can do virtual tests and physical tests. So this is more or less the structure of the project. I will be mostly focusing on work package 3, the construction of the EnergyPod, because that's where we worked in. So there are several different partners that work there. Heliox is the leader that was constructing and designing the architecture. We as TNO were providing insights and we were leading the project on integrating post-quantum cryptography. And NXP were providing the hardware, and most of the partners were doing penetration testing and ethical hacking. So a little bit on the EnergyPod. So the idea is to, I will talk a little bit later on what actually is the EnergyPod, but the idea is to have this kind of architecture in more than 100 cities. It is at the moment mostly focused for electric buses. So you're going to have a fleet of electric buses that are being managed by a remote system, which is included in the EnergyPod, that all will be charging at night, and they will be managed, and the time schedule will be managed remotely. I know that there are already plans to integrate the EnergyPod in Eindhoven, and there's going to be routes already being designed from, say, the central station to the airport with a few stops in between. There are a few requirements of the EnergyPod, so especially for the electric vehicles that are, needs to be basically secure by design, and then should be able to connect the electricity grid and the vehicle infrastructure, and everything should be basically secure by design and interoperable. So this is a little bit the idea of the EnergyPod. You're going to have a few partners on the top side, which collaborate and share information and insights on the status of the electricity grid. For example, you're going to have the balancing service provider that is going to provide insights about the cost of the energy, and the distribution service provider on the congestion availability of the electricity. And the charging point and the public transport operator are going to provide the insights on the availability of the charging stations and the scheduling of the buses. So all these insights are going to be shared and worked in the EnergyPod, and it's divided into two parts. So the EnergyPod control, which is like more the software part that happens in the cloud, where all this information is shared and a schedule is made. And this information is going to be sent to the actual charging station, which we call the EnergyPod on site, which is a set of charging stations which are controlled remotely, that they will be charging the electricity buses. So we were our role was to migrate or at least put post-quantum cryptography into this infrastructure. So as TNO, as John already mentioned before, we work on the PKCU migration handbook that has a lot of information about the migration process in many different aspects. There is a QR code of the link if you're interested. And one of the things that we try to recommend is, when do you need to migrate? So the recommendation that we give is, if you're dealing with any or more of these use cases, then you should migrate as soon as possible. And since in this project we are dealing with the energy grid, which is critical infrastructure, and the charging stations are hardware which is long-lived, then you have to migrate as soon as possible, because the requirement is that the EnergyPod is future-proof. So this is when you should start, but when you should end. Recently, the European Commission has published a roadmap on the timeline by which you need to have migrated. And if you're dealing with high-risk use cases, then you need to be migrated by 2030. Then we were looking at the architecture, and then we were trying to figure out where to start with the migration and getting some information. So we were targeting the open charging point protocol, which is if you remember the EnergyPod, there is an arrow that connects EnergyPod control and on-site, and that communication is done by the open charging protocol. So there is a link to the open charge to OCPP, as we call it. It's an open standard which is maintained by the Open Charge Alliance, and it is it is the responsible for the communication between the cloud and the charging stations. And it is based on the omnipresent TLS protocol. So we were trying to look at possible ways of migrating it. So what we did, we took a Python implementation of this protocol, which was provided by Mobility House. It is open source and online, available on GitHub. So what we did was trying to enable post-quantum cryptography in this Python application, and then we were trying to link it to available libraries. First, we were modeling it with Docker containers. Then we moved them to Raspberry Pis, and then once the Raspberry Pis were functional, we were transferring it to the actual NXP boards that were going to be deployed in the charging stations. And after that, Infiniot, one of the parties in the work package tree that is responsible for overlooking the status of the architecture, they proposed to integrate it in their dashboard. They have a dashboard that allows you to keep an eye on what is happening in the infrastructure. And then we tested several use cases, several migration scenarios, and what would happen if some of the assets were migrating to post-quantum cryptography and some not. So yeah, again, we started with a Dockerized Python implementation. We use Python linked to OpenSSL 3.5. We did try to link it to previous version of OpenSSL that were not supporting post-quantum cryptography and using OQS provider for the post-quantum cryptography. That was a nightmare. So if there is anybody that has contributed to OpenSSL 3.5 and the introduction of post-quantum crypto, thank you, because it was a very big relief for us. The idea was introducing post-quantum cryptography for both the key exchange and the digital signatures. And then we tested it on NXP board. So here you can see that we were using OpenSSL 3.5. At least they have a pre-installed hybrid, by default, a hybrid CAM. For the hybrid signatures, we were using OQS provider that supports the composite type of signatures that were presented by David and Thomas yesterday. And yeah, so you can see here that the CAM algorithms we were going for X25519 MLCAM 768. And for the signatures, we were using MLDSA, and there was in hybrid mode that was of course provided by OQS provider. So as I again mentioned, maybe we can start with the demo. So I wanted to bring a demo, but it was very difficult to take all the hardware here. So I have a recording of the communication. So here we were testing several cases in which several participants were using different algorithms. So in this case, you have a central management station and a charging station, and they were both being able to communicate using the same cryptography. So both were supporting hybrid post-quantum cryptography. So here you can see that in the demo, the requirements are satisfied, so they can communicate, and then the communication starts, hopefully soon. And then during the communication, we were trying to log the use of post-quantum cryptography, and I will get there in a moment. Should start soon. Come on. Yeah. So here we are starting the central management station and in hybrid mode. And we were able to have a successful communication using post-quantum cryptography, with the two parties. So you can see in the logs we are using a public key algorithm and a signature for the authentication part. And unfortunately, we were not able to log the key exchange in the logs. So to be able to do so, we had to use the OpenSSL connect command, and then you can see in this use case that we were able to use a hybrid CAM. And for the next one, okay, yeah. So here we were mostly showcasing what happens if one of the two parties is not able to communicate using post-quantum cryptography. Of course, what happens. So there is, the negotiation of the key exchange fails, but the other parties involved in the project, they did not know, so we needed to educate on the possible outcomes of not migrating everything at the same time if you were using what is available at the moment right now. So again, here you have the central management station that supports OpenSSL 3.5 and OQS provider, and the charging station was not supporting any post-quantum cryptography, and OpenSSL version was 3.0, so it did not have a post-quantum cryptography at all. And then should start soon. Yeah. So in this case, the communication starts and it fails because they were not able to negotiate a cipher. So yeah, we were trying to log everything that was going on, mostly because the dashboard that was provided by Infiniot, the way that it was collecting data was from server logs. So in order to provide information about the use of quantum cryptography, we needed to fill this information in the logs that were provided. So it was very difficult to record everything that was going on, that is going on during a TLS 1.3 communication, because after you exchange, you make a negotiation, everything is transmitted encrypted. So we needed to find a way to basically load the certificate in the server and inspect what kind of cryptography it was used. So yeah. TLS is used. It can be used in Python, but does not provide automatically logging information. So we had to provide them ourselves, at least for the signature. We were not able to, again, as I mentioned, to record the key exchange, and that can be done via packet sniffer like Wireshark. And again, when you look at the packet capture of Wireshark, it provides you with a code that relates to the hybrid cam, but it does automatically map it to hybrid cam. So it's a little bit agnostic on. It doesn't really know that a hybrid key exchange is being used. So this is the dashboard that is provided by Infiniot, and you can see that this provides a very an overview of what charging station is occupied and charging, and thanks to the logging that we made, we were able to record at least the signature and the public key that were used. It also happens that the communication happens only using pre-quantum stuff, and that communication would not fail, but at least the dashboard would be able to track which assets have not yet migrated to post-quantum cryptography. Yeah, and this was, for example, the use of a non-hybrid public key and signature. They were both recorded in the dashboard. Yeah, here is, since I could not take the hardware, at least I can give you some pictures. This is the NXP board that was using during the test. And that was, after the integration with the, after being able to use a Raspberry Pis to set up the communication, doing it on an XP board was pretty straightforward. So OQS provider and OpenSSL were working perfectly. As you see here, we are able to show a connection between a remote central station, which was modeled by a laptop, and the NXP board, and we were able to get heartbeats. And you can see at least in the logs that hybrid authentication was used. And this is the live version of the dashboard. So a few takeaways. After migrating to OpenSSL 3.5, everything was nice and smooth. So please, if you are planning to migrate, at least install OpenSSL 3.5, because that really made our life so much easier. Then after that, yeah, it was pretty straightforward. The problem of not being able to use hybrid certificates is that there is no standard, so they were not immediately implemented in OpenSSL. But that was okay, because OQS provider worked pretty well. It's just like if you want to put it in production, that's gonna be a kind of a bottleneck for you. And during the logging, we were thinking. We were able to log cryptography as a first step. So to monitor the transition, right? We were downloading, or at least we were generating logs that were concerning cryptography, so that we at least could have an overview of what cryptography was used. So we were thinking, is this a question that we have to you? Is this something that you already do? Are you logging cryptography? If not, why? If so, what are you doing? How are you using it? Are you using the same approach that we are using? So that was, we're thinking, is it something that should be introduced as a new sort of best practice, the log of cryptography? That's a question that was wanted to ask you. And with that, that's it. Thank you. If you have questions, feel free to ask them.
Yes. First, I'd like to see if we have questions from the audience.
Thank you for the presentation. I have a question. Now you're logging all the cryptographic information. Would it be better to use an O-bomb or a C-bomb to provide that information to the dashboard, or would you still prefer logging?
Good question. So that happens, during a live session. So every time there is a session going on, then it gets automatically logged and fed into the dashboard. So it will provide you with a live use of cryptography. C-bomb is definitely important to have, but in my opinion, but Basil can tell me if it's correct. It does not do it dynamically. It provides a list of an inventory that what is there and what depends on each other. Both of them would definitely work perfectly, I think.
Good. Any other questions from the audience? And then we'll see if there are any online questions. Anyone? So far, so good. Blair, any online questions? No? Okay. Well, thank you very much, Alessandro. It was a very interesting presentation. Warm welcome for Alessandro.
Thank you.
How do you get to a quantum-safe state? That depends on the current state of your digital security infrastructure, as well as your level of visibility, control, and automation over those systems. Check your level of preparedness with the Entrust Post-Quantum Readiness Assessment. Whether you're already on the path to quantum safe or just beginning your journey, Entrust can equip you with the right knowledge and solutions. There are many paths to a quantum-safe future. Secure yours by taking the Entrust Post-Quantum Readiness Assessment today.